Okay, everyone see my screen?
Yeah, we can see it.
Okay, just we wait a bit, another 1 minute. So if other guys join us. Okay, so, guys, do you have all of you have Schrodinger installed on your computer or laptop?
Yeah, I do.
Okay, perfect. Because we are going to work or starting preparing file for the simulation. Actually, we are going to start today. We are going to go through some basic or introductory about the molecular dynamics simulation using Amber, and then we are going through a project. So at the end of the project, you actually should simulate a correct file, and then after simulation are done, we are going to analyze the file. So I'm preparing for the docking and other stuff. Okay.
Okay.
So I believe all you find the structure on actually search on a play with a PDB data bank to find the structure. Yes.
Yeah.
Okay. Do you have any problem with that or all good?
No, it wasn't that difficult.
Yeah. So we could start. So the the previous section, we talk about molecular dynamic simulation and how actually molecular dynamic simulation could work in a simple way. That is, we have a specific force field, which is contain a mathematic formula or algorithms, so that it actually creates a create a base that all molecule had a starting, give all the molecule atoms and a starting velocity and a starting time, and then calculate first that each atoms could experience, and then solving Newton's second law for each atom, and actually, and after that, giving a new velocity to each atom, and then calculated uh, the next position of the each atom, and repeat that step for the specific time, step time. In the case of the amber, we are always using 2 femtoseconds for solving these actually equation. And after that, all these data would actually save in a specific file. We call it a trajectory file, that we use this trajectory file for other analysis. So today we are going to find how many software we have for MD simulation. The first software that actually is free is GROMACS. GROMACS actually is a good software. It's a free. It's have a great supportive thing that we could use that. But for the or purpose and for the John team, you almost use Amber. Amber is a commercial MD software. This is so powerful and so compatible for the Schrodinger. And also we have a charm. We use charm for stimulating building protein. The first thing that you need to think about when you are going to start or decide to start MD simulation is that which software would be the best for your purpose. For example, uh, you need to find each software has a specific force field or force field that I will go to the force field lately. So um, the each software has a specific force field. For example, Gromos could support its own force field. For example, Gromos, and Amber has also a specific force field and the chart. You could use the Amber force field in the Gromax, okay? But it's more compatible if you use Amber force field in the Amber force field. So if you, for example, for the simulating membrane, we should use charm, okay? So so it's better because it's better to use charm force field in the charm rather than using charm force field for calculating the lipid or other bilayer using Amber. And also Amber is a really great software for actually simulating simple acoustic system that contain ligands and metal ions. But you could simulate this kind of system on the Gromax, but you should use Amber force field. So I'm not saying that using Amber force field in the Gromax force field, Gromax software, using Amber force field in Gromax software is not correct, but I mean it's more compatible to use all the force field in the specific software that designed for, okay? So we are go through the Amber first, and if for the after finishing this project, I could give you simple project using the Gromax. So Amber and Charm is commercial, so you need to have a specific license to do molecular dynamics simulation in Amber, but Gromax is free. So for the MD simulation using Amber is such all these computer programming and simulation means all about input and output. Actually, we prepare some input and put it on the MD simulation using Amber, and it's gonna give us such outputs, and we start analyze on the output. So it's not a big deal. It's all things about input and output. If you create or prepare your inputs properly and correctly, you won't have any issue during the simulation and analyze after getting the output. Okay, that's why I told you that preparing a good starting structure is super important. Sandrer is a main simulation engine for the Amber that it takes two specific actually input file. The first input file is topology file. Topology files is actually contain all the information about your system. For example, the topology file that we are going to build in this project would contain all the information of the protein. For example, what's the protein name? What's the position of each atom in the starting structure? How many ligands we have? So the information about the ligands and information about metal protein that we are going to add to the system, because we are going to simulate a metalloprotein. And also if what type of the water molecule you are using to create a buffer for the system or something like that, okay? You are go through this information step by step. So another input file is a restart file. Restart file is super important because, for example, you made a topology file and run MD, okay? So because of unknown reasons, for example, the server shut down, the electricity gone, that's something like that. So you do not lose your file. Okay, you have these restart files, so you could restart your MD using this restart file. Okay, so be sure. restart file actually gives us an opportunity to restart or simulation on a point that the Orion gets killed because of the unknown situation or other things. Okay, and so another things that using when you are going to use Amber as a MD simulation software, as it's something like TLIP. So what's a TLIP? You actually prepare all these topology files using the TLIP. Is a program or helper program in Amber. So this TLIP actually takes the coordinate files such as PDB that we prepare, we download from the PDB data bank and preparing after that, and also ligand information that we need to actually create by a specific software, a specific program, and then use these input file to generate a topology file and restart file. So we could use that topology file and restart file as an input for the final MD or production run. Okay, so in the simple word that TLIPs takes the PDB and other a structure file or coordinate file as an input and create topology file and restart file as an output. And then we use these output as an input for the production run. Okay? So another question is that why we need TLIP? Why we couldn't use this coordinate file as an input for that? So why we need use TLIP to create topology file and restart file? So actually, Amber has a lib. Lib is like a library. Okay, Amber Amber software package has actually similar library files. It's like a library for the standard amino acid. So if you actually look at the PDB file, okay, you see something in the PDB file named atom. This is all these standard amino acids or nucleic acid. So other things except one that's named atom in the PDB file is non-standard. So you see the non-standard residue as a heteroatom. You see that actually if you look at the PDB file, you see this file. So Leap actually should merge all the information in the PDB file and the lib file together, because all these, that's why I mentioned that preparing the structure, starting the structure, PDB file is super important, because TLIP should actually check the information in the PDB file with the library file in the Amber. And these two files should be compatible and matching residue name. So for example, if you have a residue in a PDB files that have a specific name, for example, arginine in the, not arginine, let me see, let me give you another example. For example, in the PDB file, the name of the water molecules is the H2O or something like that. Okay, but the Amber library, in the Amber lib files, the water molecule name what's in the all capital letter. So if this file and this file is not compatible, or the name of this residue was not matching, so Amber couldn't recognize water molecule. So and therefore did not add water molecule in the topology file. So give you so many errors. Okay, so, and also another thing that's super important is that in the we have, if you check this PDB file, you have some charge residues such as arginine, lysine, histidine, and so on. This residue base of the pH that's recognized, that actually puts base of the pH that these amino acids exist in this environment, the side chain could be deprotonated or protonated. And the amber has a different name for these protonated and deprotonated states. So we need to actually find that, for example, we are going to work in a body pH, body pH. So before the starting simulation, we need to calculate, or we need to prepare PDB file so that all these chart residue has a correct protonated or deprotonated state. So it gets compatible with the lib files in the Amber. So we go through this step, later when starting preparing file. I just give you some information that why we need to do that steps. Okay. So so I told you that Amber libraries have a specific lib files for all these standard amino acid or standard atoms. So how about the heteroatoms that actually exist in a PDB file? If you want to, we have ligands, we have bottom molecules, we have metal ions that for having a realistic simulation, we need to have all these non-standard residues as well in your system or a topology file. So how we should add these files? Okay, the Amber actually has a program named Antichamber. So this Antichamber, so as I mentioned that there is no lib file for non-standard residues such as ligands and rare amino acid. For example, in the upcoming actually a project that I will give you, you have to care for specific rare amino acids in the Amber. So for having a specific coordination, you need to learn how to treat with these rare amino acids. So actually in Amber, we need to create lib files. So because Amber have no lib files for the non-star residues, we should ourselves find or create these lib files by ourselves. So we create lib files using the specific Amber programs named Antichamber. Okay. So another actual measure that need to be explained is about force fields. So what's the force fields? So in a molecular MD simulation, in the MD simulation, each molecules would be described as a series of the atom. This is a series of the atom that link by bonds. So to describe evolution of the bind lengths, so each binds has a specific lengths and angles and torsion, and also we have to specifically identify non-bonding van der Waals, because for example, even though these molecules attach or links using a specific bind, there is, for example, we have so many molecules in the system. So each molecules could interact with each other using non-actually van der Waals and electrostatic interaction. So force fields is a term that actually have a specific equations, it's mathematic equations and specific constants that design to care or treat or about these molecules. and actually define these bond angle, torsion, and lengths that we actually input to the software. Okay. So in the classic force fields, each molecule could be described as a collision of the many atoms. Okay, you have this, you have a actually PDB file. Each PDB files have a specific residues, so many residues. Each residues contain atoms, certain atoms. So force fields should contain all the information about angle, bonds, dihedrals, and also it also needs to care about non-bond interaction in terms of electrostatic and van der Waals. So we could care about these terms too. This is actually is a terms and this is abbreviation. That's in a simulation files mainly you use this abbreviation. So the important things that you need to things that do not confuse about how to use Amber, because these especially apply to how to use Leap program works. It's a simple ways that actually leaves each of these files. I mean, PDB, mode2, leap, prep, that's RC mode. It's all contain part of information that you are need to performing uh, uh, a main MD that contain minimizations, equilibrations, and the production run based off these classic force field that actually contain or care about these bound angle and something like that. So we first need to use or prepare that file and put it this file as a input to the Amber, so that Amber could use these file as a actually inputs for each piece of information. It's like a puzzle. Each file contains a piece of information that we require for the MD. So Amber, after starting to the first actually after starting the main simulation, Amber actually generates a topology that contain all this information and start to simulate our system. So this is the main step of each simulation in a simple way. The first step is preparing the structure. It's super important because if you do that correctly, you have no worries, because another all these actually next step is just such a comment. This comment is universal and just something sometimes you need to change a bit these comments, but overall the same. These comments is same, and I will give you these comments so that you actually just copy paste these comments. It's not a big deal, but it's important that you know or you be aware of what are you doing. Okay, so first you need to prepare the structure, and then we need to add in water and iron. So why we need to add water? So in a cell, all the protein exists, actually almost all the protein exists in an acoustic environment, except the membrane protein that's also this membrane protein is water too. So we need to add water to have a realistic and to add dynamic to the system. Without the water, actually we couldn't see any movement. And also we need to add iron to balance or charge. All these protein have a specific charge residues. So for in a realistic system, all these charge residues should be balanced. So we add ions, counter ions. For example, if the overall charge of system is positive, we need to add counter ions so that we could balance our charge. So another, just freezing, okay. The next step is energy minimizing. So when you add preparing a structure and adding water and ion molecules, system contain clash. The energy of the system is not converged or not good, because in this system, all these molecules could clash to each other. So if you don't minimize the energy, all these actually system could be crash, and you get error, and you couldn't actually have a good and realistic files. Okay, so we need to be sure that all after adding water, we need is a fundamental that we need to first minimize the energy before starting the production run. Okay, and then we need to equilibrate the system. That means that the pressure should be constant and the density should be actually okay. We check the density, we check the temperature, we check the actually pressure. So after checking all this step and finding that all things is okay, and then it's create the files for us, and we'll create the files for us to allow us to starting production run. So after production run is finished. So if you're preparing the structure well and preparing the topology without any errors, you could be sure that you will be fine and you will have a good production run, and you could start analyze. Okay, so let's review the actually a structure of the PDB files. So as I mentioned, the PDB files is contain the atom and heteroatom. This atom is all this not standard residues that actually Amber has a lib files for them. So we don't need to actually worry about this file if we prepare that. Okay, and this is an index file, and this is the name of the atom. For example, the first atom named N. Okay, this is important because, for example, each program, each software, for example, Charm, Duramax, and Amber, even though it has similarity, but each one has a specific naming system. So you need to find, for example, if you want to do the simulation using Amber, you need to first find the specific naming format for the Amber, because if you don't care about the naming system in Amber, Amber could not recognize your files, and you are given errors. So, and this is a res name, this is residue name, and this is a chain. For example, sometimes when actually, guys, if the time is over, just use the same link, okay? Okay, sorry. So, when a crystallographer crystallize a protein, maybe in some crystals, you have more than one protein. For example, you find a files, it's contain 3 or 4 or so of the same protein. So you use one of these chain, okay? This is chain. For example, this structure contain 2 or so chain A and B, for example, and this is chain B. For example, if you want to simulate using this chain, your chain name would be B, okay? And this is a residue number. This means this is the residue name. This is the third residue in this protein. And this is the XYZ this is for the location of the actually atom, this atom. I said that I told you that each atom has a specific actually position in the 3D. Yes, and this is the initial. This is the initial actually. This is the initial location in the space. And after that, using the force field and MD simulation, we are going to add velocity, new velocity to each atom, which creates a new position file that this is actually the main point of the MD simulation. We grab an atom, this is a specific position, and the velocity at the first and the first velocity is 0 because it's not moving, and we put it in the MD simulation actually using the Newton's law. Software adds new velocity to the atom and predict the new position in the space for the atom. So this atom, we are going to create so many new positions based on this relation and non-bond and other parameter that Amber care about. We not need to worry about how to actually create the position. The software automatically using the input structure and the force field that we mentioned in our files, create this new file. And this is the main important feature of this structure of files. Why is freezing again? Okay, so after creating all these input structure, I mean the PDB file, and decided which force field we are going to work with, we need to create a topology file, okay? As I mentioned, first we need to prepare a structure, and then we need to add water and ion. After adding these files, if you need ligands and other things, after that, Amber creates for us a restart files and the topology files that we grab these topology files and put it for the energy minimization. Okay, so for the topology file, I mentioned that we need a helper program named TILIP. So this is a TILIP sample files that you are going to use with. In the source that's actually creates, it's mentioned that which force field we use for the protein that is started for the standard residues. It's a lib files. Just care about thinking about as a library. We use these force fields to care about all these angle, bonds, non-bound, van der Waals, and other structure. And this is the gap for the water molecule. This is a universal Amber's force fields that care about the water molecule and ions, okay? So after that, this actually tells the Amber that please loads water and ions for the farms. This is a parameters for the ion and actually waters, okay? This is for the ions. So needs to actually load the parameter for the ions so that the Amber could recognize ions. Without that, you get me if you do not load these and then just add ion, counter ions, you give error because you don't know the Amber couldn't recognize the ion without these loading the parameters. And also in that, you tell Amber that I'm going to use these type of the molecules for the water. Please load the parameter for these type of the water molecules. And after that, if you have a specific ligands, as I mentioned, you need, because ligands, GTP, GDP, all the ligands you already docked, for example, in the protein is non-standard. So the Amber has no any library or lib files for these non-standard residues. So we need to create or build the lib files for that. So as I mentioned before, we use AnyChamber program to create these files. So after creating these files, we use that as an input for the lib files. We say that, okay, no, I create these files, create the libs files and parmatch files for my ligands. So use these lib files that I prepare by myself. Okay, after that, this is another ligands actually. And after that, we need to put together all the protein, ligands, and all things that can put together all the standard, the protein, and non-standard residue together. And then this is our final, that's load PDB files for all that contain all the information. I mean, all these residues, both non-standard and standard residues. And then because I told you that we need to balance or charge or system charge, we need to add counterion. For example, if in that case, I found that actually I find that my overall charge for the protein would be negative. So I need to add positive charge Na, positive charge ion, okay, that make the charge of system 0, okay? And also Amber could, so so if we add ions, actually Amber automatically replace ions with, after adding actually ions, Amber automatically replace water molecules with a charge or ions. It could not actually replace one of the specific residue, for example, protein residue or ligand residue with ions. And after that, we create a box. This is a dimension of the box and type of the box. And this is the water molecules that we are going to use. Okay, first we could this actually tell Amber that please create a box in that shape, in that size, and fill it with these type of the water molecules. And after filling these box with water molecules, create a topology file and coordinate file for us. Save the coordinate files and param files. And then click all clear.